Take a look at all that. Go ahead. See what you got to do. Oh man, yeah, big idea five, folks. We're getting there. We're working on the downward half here. We're going to talk about applications of definite integrals. Oh yeah, they're back. Remember those? I got some videos. If you don't remember what a definite integral is, go take a look. They're there because you're going to need to know about definite integrals. Going to need to know how to graph, and you're going to need to remember some of the geometry ideas that you learned eons ago. You know what? Speaking of geometry, let me throw you a slow ball here. Let's find the area of the shaded region. Remember those problems? Oh yeah. Find the area of the shaded region. Well, if we got a circle that's inscribed in a square and the radius of that circle is 3 centimeters, then all we got to do is take the area of the square and subtract the area of the circle. It's pretty obvious as the game plan. It's the whole minus the whole thing minus the hole that we cut out. Otherwise known as the bigger area minus the smaller area. So the square, well, if the radius of the circle is 3, then the diameter of the circle is 6, which means the side of the square is 6. So the area of the square is 36 unit centimeters squared. Subtract the area of the circle, which is pi times 3 squared. There you go, 36 minus 9 pi. The idea of bigger minus smaller is you're going to see that repeated throughout this lesson. So what are we going to do when we ramp this up to calculus? That's an old problem. All new math is old math repackaged. So like, how are we going to ramp this up to calculus? Well, we're going to graph functions, right? We're going to graph here these functions 4 minus x squared and the linear x plus 2. And we want to see what happens to the region that is bounded by those two graphs. So here in red, you see the region that is bounded, a planar region, like a region on the plane. How do we come up with the area of that figure? Well, the idea that goes back to that old geometry problem, find the area of the shaded region. We want to take the bigger area and subtract the smaller area. We know that definite integrals, while they aren't exactly area, they do find area for us. So the plan is this, right? To find the area of the red region, we're going to find the between the two intersections, right? What's the area under the parabola? We're going to find the area under the line, and then we're going to subtract the bigger area and subtract minus the smaller area. That will be the resultant region that we want. So we can do that using definite integrals. So you can see that the intersections -2 and 1. We want to find the area under the parabola. So that's this little guy right here. That little guy right there. Yep, that first definite integral there. Subtract the area of the triangle, which I know I didn't need a definite integral, but you know what? I did one anyway. So there you go. Since they have the same limits, right? You can combine those together into one definite integral. It should be equal from -2 to 1 of the function function I declared as b of x. I did that for a reason. T and b, top and bottom. That's going to be a recurrent theme. The top minus the bottom. All right. Now, we look at that picture and you're like, okay, right. Yeah, that's kind of obvious. It's the bigger area minus the smaller area. But one thing you all got hung up on, at least at first, was what if the functions are negative? Doesn't that like change things? Because definite integrals of negative functions are negative, right? It's not, definite integral is not area, right? It is a product, right? So if we integrate to the right, a function that is negative, we get a negative product. So how can area be negative? Shouldn't we switch some things around? Like, what if the functions are negative? What if they're some positive, some negative? Like, what do we do? Well, long story short is nothing. You keep the same plan of attack. What's the top function? What's the bottom function? And just do the integral of top minus bottom. There's no flipping around of who's further away from the x-axis or anything that you're thinking, because it works out like this, is that if I have a function, two functions that are negative below the x-axis, the definite integral is negative, sure, but negatives work like this. If the definite integral for t is -3 and the definite integral of b of x is -5, then we still do the bigger minus the smaller, right? The bigger is -3 minus the smaller, -5, that gives me a positive value. There is no switching, right? So what if some of it is negative and some of it is positive? Well, it doesn't matter, because you can split up definite integrals into component pieces. So if you need to, which you don't, you can just split up definite integrals. So you're just taking the positive piece and the negative. What am I trying to say here? Don't do anything different. It's always the bigger minus the smaller. Thus, it is always the top function minus the bottom function, the definite integral of that on a to b, right? As long as t is greater than b on a to b, the interval. Now, if we're in terms of y, things are similar, right? The story is bigger minus smaller. Now, top and bottom, okay, top is bigger, but right and left, who's bigger? Which has a bigger x value? The right side has a bigger x value, so that means the right side is bigger than the left side. So for functions in terms of y, I'm just going to do the integral from c to d of the right minus the left, where that is bigger minus smaller. That same motif throughout this whole entire unit, really. When we talk about volume, we're going to talk about bigger minus smaller, top minus bottom, right minus left. You're going to see that over and over again. That's the idea that you should the key idea that you should keep in mind, that it's bigger minus smaller. So there's those two integrals right there. Let's kind of put them into practice. Okay, so we're going to find the area of the region bounded by y equals x squared and square root of x. You need to graph the sucker, all right? Don't just go like, I don't have to graph it because I can picture it in my head. No, graph it, see it, draw it into existence on a calculator, on Desmos, sketch it on a paper. Please draw it so you can see what's happening. All right, so here is that little region, little leaf-shaped region, right? So we want to find the area of that region. So we need to think about, well, where are the intersections? The intersections between x squared and root x, well, it's pretty easy to solve. That's going to be at x equals 0 and x equals 1. Well, the top function on 0 to 1 is root x, and the bottom function on that interval is x squared. So then we set up the integral. Pretty easy. The integral from 0 to 1 of the top function minus the bottom function. So that is going to be the integral of from 0 to 1 of root x minus x squared, which that is 99% of the battle. Then we can just evaluate the definite integral however we have to. Right here, I can do it by hand. It's not that tough. But I can also just grab a calculator or technological device and zippity-zappity zoop and get it evaluated if I need to evaluate it. Same with the intersections. I can get the intersections on a calculator really quickly if it's not easy to do by hand. This one, pretty easy. All right, let's see another one. Oh, wait, warning. Before we see another one, here is a problem that a lot of students have. A lot of students, they disregard all of that bigger minus smaller talk, and they just take one function and subtract the other function. Here's what that's going to do. If you take the smaller function and subtract the bigger function, you're going to get a negative number, aren't you? Yeah. And if you integrate a negative thing, you get a negative thing. So to fix it, an area's got to be positive. Well, I'll just make the final answer positive. That's not a good place to be in, okay? That's like saying the absolute value of the definite integral is equal to the definite integral of the absolute value. We talked at length about how that is not a good place to be in. In fact, I'll even show you again, like why it doesn't work that way. So if you think about just sine x on 0 to 2 pi, right? If you want to think about the area of those two red little regions combined, not the definite integral, the area, right? You would have to do top minus bottom. You could do sine x minus 0 on this first little hill, but then you'd have to do 0 minus sine x on that next little hill. Well, guess what? If you integrate from 0 to 2 pi, just sine x minus 0, you get 0, okay? Now, if you do it the right way, let's say you absolute value sine of x minus 0, more on that later, you get a total of 4. Now, I'm no math teacher or anything, but 0 and 4 are not the same in my book. Now, we get two totally different answers, so don't just make your final answer positive. Make sure you take care in setting up the integral correctly. If you don't worry about setting the integral up correctly, don't be like so surprised when you get wrong answers, right? Heed that warning, ladies and gentlemen. You need to set things up right if you want to get them right. All right. Moving on. Now we need to find the area of a bubble that exists between sine x and cosine x. There's an infinite number of bubbles. So let me show you what I mean by a bubble. This is what I mean by a bubble, just one little region between. Now, as far as this little region is concerned, right, sine x and cosine x are the same in the first and third quadrant. So pi over 4 and 5 pi over 4 would be the intersections. I could do any of the other little bubbles. They're all going to be the same. But I'm just going to take this one from pi over 4 to 5 pi over 4. Now, on that interval, sine is top and cosine is bottom. You might notice I've got this little thing here, the height of the representative rectangle. So these little rectangles, if you remember when we talked about Riemann sums and how we defined a definite integral, it was a bunch of little rectangles in there, and those little rectangles are all sliding along. The height of any one rectangle is the top function minus the bottom function. And remember, we integrated height. Here we're going to integrate height, where the height is top minus bottom. So we set up the integral. The integral is from pi over 4 to 5 pi over 4 of the top sine x minus the bottom cosine x with respect to x. Look at all that good calculus. Oh boy. Or you can just get a calculator if you're scared of trig. You can chicken out and get a calculator, or you can verify, hit the pause button, see how all that is right. If you went ahead and hit the pause button, you can verify that that is wonderful. Yeah. Yeah. Well, here comes one in terms of y, right? You're going to see these occasionally. Occasionally, you get some in terms of y. So we want to find the area that's enclosed by the graphs of x equals y to the fourth minus y and x equals 4 minus y. You're probably not a pro at graphing things in terms x in terms of y. So Desmos is your friend. I did that on Desmos, right? And the height of the rectangles, now the height is like sideways. So we want to do the right side minus the left side. The right side is the linear. The left side is the quartic. So when we set up our integral, we need to figure out what these intersections are. Intersections in terms of y, right? What are the y values that they intersect? So the y intersections are positive root 2 and negative root 2. So then I want to set up my integral from negative root 2 to the positive root 2, so from the bottom to the top, the right side minus the left side, right being the linear 4 minus y, and then minus the quantity of the left, which is that quartic function, y to the fourth minus y. Now that's fairly simple setup. It even simplifies nicely to this, which you could totally do that. Antiderivatives 4y minus y to the fifth over 5, plug in all those numbers and get an exact value, or you could just fudge it and put it into some kind of calculator, which is what I did. All right, another example for you. Now here's where it gets interesting. So come back, put the switch down, come back. let's pay attention here because, oh my gosh, what happens in this one? This one is kind of new and different. The region that is enclosed by the cubic h of x and the linear f of x, you look over here on that picture, and oh my, look at that purple area. Huh. Well, they flip-flop, right? They flip positions, who is top and who is bottom. So the intersections, -2, -1, and +1, well, on different intervals, on the interval from -2 to -1, the cubic is on top and the linear is on bottom. But then from -1 to +1, the linear is on top and the cubic is on bottom. So I'm going to set up two separate integrals to make sure that I account for that flippy floppiness. So there you go. -2 to -1. I wanted to do h minus f because that was cubic minus linear. But then on -1 to 1, sorry about that, -1 to 1, I want to do f minus h. So, what's it going to be? Well, there you go. I just hit it with technology and got 3.083. Approximately would be a nice number there because that's repeating. It would be a nice rational answer. But here's what we can learn from that bogus thinking that I talked about earlier, how we can't just do one and subtract the other and not really care, and then just whatever the answer is, make it positive, especially with the flippy floppy. Because if I do the integral from -2 to 1, so all the way across of f minus h, and then take the absolute value, I can only get 2 1/4. Now that's not right. But if I integrate from -2 to 1, the absolute value of the difference, I get the same answer that it should be. So is there some kind of shortcut? Is there some kind of cheat for the system here that I can just make sure that I get the right area for any region without worrying about who's top and who's bottom? There is. Here's why there is. Right, because the goal of the integrand function is to make it positive. Remember me talking earlier about taking care and who is top and who is bottom? It's the bigger minus the smaller. And we do that to ensure that the integrand function is positive. And we want it to be positive because we want to integrate in the right direction a positive thing to get a positive answer, because area is always positive. So the height of any one of those representative rectangles is a distance, and a distance has to be positive. And you can guarantee that that will be positive doing two things, okay? One, doing the top minus bottom, all right? So all of this over here, right? Making sure that on the interval, I pick the top, I pick the bottom, I put them in the right order, I make sure all that is hunky-dory, and then I move on with life. Or I disregard top and bottom. There might be flippy floppy, there might not be flippy floppy. But all I need to do is take one function, subtract the other to get the difference, but then hit it with an absolute value. And that ensures that all those heights are positive. And then I have to integrate that absolute value. So two options here: make sure that it's top and bottom and set it up in that right way, or hit that difference with an absolute value and then integrate, and then you know you're going to get it right. So I've kind of given you just an idea of how to do it two different ways, but like maybe one way is better than the other. If you're just pencil and paper, I would suggest the top minus bottom, making sure you do it right. If you've got technology, you got a calculator, you can crank out a definite integral of anything with technology, and that absolute value is not going to matter. So if you have paper, if you're just by hand, I would suggest doing it right. If you got technology, you could do either way. It really doesn't matter. That's pretty cool. That's pretty nice. So check out this last one here. All the flippy floppy action, right? We need to be able to do something quick. Peep this. All right, I came up with these two crazy looking functions. Look at this crazy looking caterpillar here. I got two functions, some linear plus cosine, and then g of x is x minus sine. It's craziness. I had to play around with it for a while. But you got one, two, three, four, five. You got six different regions. The red regions, that's where G is on top. In the orange regions there, that's where F is on top. So you could do six different definite integrals, finding one, two, three, four, five, six, seven intersections and setting up. That wears me out thinking about it. So here's the plan. I'm just going to subtract F minus G. I get it first and last intersections, right? So that first intersection over here, which is 4.7-ish. The last intersection, which is almost 21, right? You want to take care of using as many decimals as you get. Setting up the integral, just integrate from that first intersection to the last intersection of the absolute value of the difference between F minus G, and it gives it to me. There it is. Boom. I bet you didn't know it was 157.573. Bet you didn't. Well, it is. Well, then I want to show you that this purpley little bumpy thing, that graph is the graph of the absolute value of F minus G. Let me show you this again. That's the picture of F and G together. This is the picture of the absolute value of F minus G. Now, what you might be able to see, if I zoom out a little bit, okay, each of the little hills in the purple function, they're exactly the same area of the picture of the real function. So like this first little doohickey guy, it's the same area as this little orange doohickey guy. And this big old purple bump right here, that's the same area as this big old orange glob. They're the same. What is this wickedly awesome here that we have a way to shortcut finding area between curves, especially with all those flippy floppy actions. All right, we've seen how to set things up easily with top minus bottom. We saw one where we did right minus left. We saw a couple options for flippy floppies where the functions switch top and bottom. We now have a way to cheat the system doing the absolute value of one function minus the other. We got some options here to find area between curves. So we can use what we know, the integral of top minus bottom or right minus left, or I can use the absolute value of one function minus the other. So you know how to find area between curves now. You're welcome. Next time, we're going to talk about how we can use definite integrals to do length. It's going to be weird because you've equated definite integrals with area, right? That's not a problem. Now we're going to talk about definite integrals to find length. Curious. I can't wait.